What I'm going to talk about is what I think is relevant to astronomers about machine learning. And as we were going to get the mimosa supplies, Foreman Mackey said, I hope you're going to say that nothing in machine learning is relevant to astronomers. Which, you know, is a bit of a strong statement, but it's close to true. A lot of the things that people work on in machine learning have no relevance to us at all. So I'm going to talk about places where they might have relevance and reasons you should be careful if you go out into the machine learning world.
What about particle physicists?
Say again.
What about particle physicists?
What about particle physicists?
Is machine learning useful to them?
Same, I would say same. It's very rare that it's useful, but there might be some things that are useful. And I will. So I'm not. Sorry, I'm not supposed to talk just about astronomy. I don't mean to be talking just about astronomy. Also about particle physics, but any kind of physics, science, quantitative science. So we work in a hard science, quantitative science, where there's numbers. So I'm going to talk about places where that matters. Okay, good. That includes econometrics. And barely includes biology, does include systems biology, etc. Okay, good. Let's go. So the first, there's many classes of things in machine learning that people talk about. One of the biggest areas where machine learning has been very successful and has a lot of techniques is called supervised classification. And the idea behind supervised classification is you have lots of labeled data, meaning you have, so in an astronomy context, you would have sources in a catalog, some of which are labeled stars, some of which are labeled quasars, and you've identified that they're stars and quasars by some external mechanism. Like God told you that these are stars and these are quasars, or maybe you took a spectrum of some and you know that some are stars and some are quasars. Or another kind of label data you might have is you might have a bunch of events in the LHC that you know are created by like 2 jets or something, and you have a bunch of events that for some very strong reasons you know are 2-jet events, and you want to label other events. So the idea is you have lots of labeled data, you have some unlabeled data, and you want to label it. So the job is label it. And the really classic examples of these are not in hard science, they are in computer science. They're like, there's YouTube videos, some of which contain cats, some of them have been labeled cats, some of them are either unlabeled or you don't trust the labels. So you take the ones where you trust the label cats and you try to figure out which other YouTube videos contain cats. That would be a standard kind of problem. And you might think I'm joking, but actually it's one of Google's biggest research efforts in the last few years was to find all the cats on YouTube, and they had some press releases about it about a year ago.
Were they successful?
Why?
Yes, they were very successful. They were more successful than any of the existing benchmarks, but I think they may have been beaten recently by University of Toronto. But one of the standard challenges right now in computer science is to find cats in YouTube videos.
Why?
Why? Mariam asks why.
Because you can.
I mean, if I have to, that's like when people put up a thing and explain why cosmology is important, and we're all like, don't tell us why cosmology is important. Anyway, okay, now, if you have, so, I have so many things, did you win?
It was.
The crowd booed the decision.
It was.
The crowd booed the decision?
I won the crowd, yeah.
So you won the crowd, right? Oh, let's hear from Mario. Win the crowd.
It was nonsense. It was as if there were no such thing as judges.
Did you beat up a lot of people last night?
No,
was there a huge brawl?
No, but I cursed a lot. A lot. So much so that one of the press officers turned around and took a picture of me screaming at the judges.
Right on. You gotta be a little careful because the judges probably are ex-boxers. Okay, good. Back on track. So if you have, here's the issue. There are a bunch, and machine learning has come up with many good methods for this problem, under the very restrictive assumption that your labeled data are statistically very similar to your unlabeled data. So that's why the YouTube video example is a good example. Even that isn't a great example because people who label their videos cats tend to be the more responsible YouTubers who are better at like shooting, editing, and uploading video and then tagging it correctly. So even in the YouTube case, it's not strictly true, but it's close to true. In the physical sciences, it's very rarely true. Right? So in astronomy, which I know well, like you tend to have good labels for your bright sources and bad labels or no labels for your faint sources, and your faint sources are observed more noisily. Therefore, they're statistically very different than your bright sources. Therefore, a lot of machine learning methods won't work. And that's kind of the origin of Dan's comment at the beginning that maybe none of this machine learning is very relevant. Because a lot of it sort of makes these strong assumptions which just aren't true in our real lives.
But even in the case of the cats, because then you want to label all the videos that feature cats, or you want to label all the videos that are about cats. So that's kind of the same thing in a way, right? So you're going to label a cat if it's a video about your cat, but there can be a cat for 90% of the time.
Good, yeah, okay, good. So actually the issue you're bringing up is there's a whole bunch of work, actually there's a lot of interesting work on the fact that you don't actually trust your labels, or the labels mean different things in different contexts. And that's true in astronomy too. People take a data set and split it into stars and quasars, and they actually mean different things by that. Different investigators mean different things. Because some people tag their video cats because it shows cats, and some because it's about the care and feeding of cats. So you're going to have a video labeled cats, which is just some cat nerd talking about how they take care of their cat. Which if you're trying to find the actual cats in the videos, that becomes what's called label noise, that these labels themselves are noisy things. Anyway, my main piece of advice here is that if you have a problem, oh, by the way, I want to say something. The particle physics analogy also has this property. The events in LHC that you can obviously label as being 2-jet events are your best 2-jet events. So if you run a sort of standard evaluation on it and then try to label the unlabeled events, you're only going to be able to label the unlabeled events which look like the labeled events, the ones that are also sort of very clearly labeled. Most labeling methods, most classification methods don't generalize well to the case that this data is worse than this data. This data is noisier or worse calibrated or whatever, worse understood in general. But if you do have the situation that you have labeled data and you have unlabeled data, and the labeled and the unlabeled data are very statistically similar, by far the best method to use is kernel SVM. Support vector machine. I'm not going to explain this method in detail. It is so beautiful. This is a very, very simple method. It works really, really well. One of the authors of the kernel trick is sitting in that office for the next 3 months. So we actually have expertise here on this particular method. But this method is just very highly performing, has very few free parameters. It just works. It is really good. We've run it on various things, including star-galaxy separation, or quasar-star separation, which I keep mentioning, and it works really well. It's just, in general, a very good method. So this method is simple, it's fast, it's effective, it's all the things you want. It has free parameters, but you can set those parameters. And here we'll bring something back. You can set those parameters by cross-validation. Remember cross-validation, which I talked about for setting model properties? Cross-validation, so for choosing among models, cross-validation can be used to set the parameters of this method. In fact, all the methods. This is the right choice. Now, a lot of astronomers, and probably also physicists, because it's so attractive, have done things which are called artificial neural nets. Artificial neural nets are another category of problem like this, of method like this. Actually, there's tons of methods like this. Another method that we've heard about in this room several times because astronomers have started to adopt it is called random forest. Do not ever use artificial neural nets. Please stop using that, everybody. YouTube audience out there, don't ever use artificial neural nets ever again. And one of the reasons you shouldn't use artificial neural nets, they're very effective. In fact, Google is about to crash through the doors because the best performing methods that find cats in YouTube videos are in fact very, very complicated versions of artificial neural networks. But the reason artificial neural networks are not a good idea is there's a lot of structure and complexity decisions you have to make in here. So even though you can in principle make all those decisions by cross-validation, you never would. It would just be a huge effort to properly set the complexity of an artificial neural network. Furthermore, training them is hard, so they're not simple, they're not fast. They're only effective if you do a lot of work on setting their structure and their parameters. So these are just not a good idea. It is a good idea possibly if you happen to be a collaborator with one of about 4 people in the world, one of whom is Jeff Hinton, one of whom is Jan LeCun here at NYU. If you happen to work with Jan LeCun, then yeah, turn it on, because you've got the best person in the world who works on it. But if you're on your own, don't even think about it. I would ordinarily have said no to random forest, but one reason why random forest is an interesting idea these days is that a bunch of astronomers and physicists at Berkeley have implemented, stats people have implemented a very simple, very fast, very effective method of random forest that's available free to academics. And I can tell you more about that if you want, but random forest is in the same category. In the sense that it relies on these strong assumptions that the labeled data are similar to the unlabeled data. Let me say one more thing about this before I move on, and that is, anytime you have a system that can predict labeled data, you can also do regression. What's regression? Well, regression is where you predict not the labels, but you predict some continuous parameters. So, for instance, say you had a bunch of galaxies for which, through painstaking analysis, you figured out their star formation rates and their luminosities. If you had more galaxies with the same kind of underlying data, you could predict the star formation rates and so on by doing regression. Because regression is predicting labels that happen to be continuous. Your labels don't have to be discrete labels, they can be continuous labels. And there's regression forms of all these algorithms. Yeah.
So, but when you're doing the classification, at some point, some high-level analysis must happen so that you know that the video has a cat in it or something like that, right? You actually have to do processing before you do a label, right?
Right. Getting labeled data is very expensive.
Okay.
So in astronomy, the way you get labeled data in the star-quasar thing is you point a $50,000 a night telescope at your objects one by one and take spectra of them.
Right.
So you spent a lot of money getting this labeled data. That's why in contexts other than hard science, this is such a valuable thing to do. Because instead of labeling all your data by that expensive method, you can label a statistically relevant subset and then expand the labels to everything.
Okay.
That's why astronomers, right now astronomers are very interested in this, because astronomers are thinking forward to like LSST, where there's going to be 10,000 alerts a night and we have to classify the alerts and decide what we want to do. So people are thinking about these kinds of analyses, and it might be relevant at some point. But right now, in astronomy, we're in a situation where the labeled data are always your brightest, best data and never representative, and therefore these methods naively don't work very well.
Right.
Actually, we're currently in a bake-off between methods I'm going to talk about in a minute and these methods for quasar versus star with machine learning. Okay, good. So let me say just a few more words about classification before I move to other areas. So why do these things not work very well in the case that your labeled data and your unlabeled data are statistically different? Well, I'm going to draw a graph, which might not be very helpful to you, but the idea is that there's stars in the universe. Thinking in the astrophysics example, just stay with the astronomy example just because I won't make so many mistakes if I write it. You believe there's like properties of stars and properties of quasars out there in the universe. You don't know that much about these things, but you know enough that you can make some kind of model of them. And these two things produce your data, but your data are also produced by noise, meaning the data have contributions to them which come from the fact that they're observations of stars and quasars, but also have contributions that come to them from the fact that there's noise. And the idea is that these stars and quasars have also produced your training data, the data that is labeled. I should have called it labeled data to stay consistent with that. So we're going to do that, labeled data. And this should really be the unlabeled data. And this also has noise going to it. So both your labeled data and your unlabeled data are being produced by stars and quasars, but they're also being produced by noise processes. And those noise processes are in general different. So if you have a model that doesn't know about these noise processes, then you have a model that's not going to perform very well. So that's kind of like a really deep thing in all of like data analysis in general and machine learning and everything else, is if there's something you know about your problem, you ought to be using it. If you aren't using it, you're making a mistake. So these methods just take the labeled data and the unlabeled data and give you some answers. You don't have to tell these methods things like, oh, it was a Poisson photon counting device and the background level was this and readout noise was this and my flat field looked like that. Since you don't have to tell it all that kind of technical details, these clearly don't know things about your problem that you know about your problem. Because you know those things about your problem, you should use them. So this gets into probabilistic modeling. So my view is that you always have to have a probabilistic model of your data if you're going to perform well, because, and what do I mean by a probabilistic model? Well, I mean a bunch of things which go beyond the standard meaning. The standard meaning of this is very, very trivial, but what I mean by this is it contains the causal structure that you know about, and it also contains noise models. And anything you know about your noise and about the causal structure of your problem should exist in your method. And we have methods that do this. In fact, the world leading method for separating stars from quasars is currently called extreme deconvolution. And this is a method that's by Joe Bovey, who is here at NYU. But this method is a method that explicitly tries to model the labeled data as coming from sources and noise, and the unlabeled data as coming from sources and noise, generate a model for this whole process, and then do the classification within this whole process. So this is the right thing to do if you know, if your labeled data, unlabeled data are very different, and you know the ways that they're different in terms of at least the noise model.
Can you include other information such as perhaps the fraction that you might expect of one versus
Yeah, exactly. Anything you know is useful. So for instance, if you know that you're trying to separate stars and quasars, but actually 89% of your objects will in fact be stars, that should also appear in the model somewhere. And this, the way it would appear in this graphical model, would be something up above here, which sets the fraction of these two things.
I have rather specific questions about this.
Go ahead.
So let's say you have an object. Let's say something is a quasar, and you run it through QSO, and you get some probability of being a quasar given the errors on the boundary.
Yeah.
Are you trying to create a model such that if you vary the errors, you still have the same probability of being a quasar?
No, definitely not. That won't be possible, in fact, because as your errors get worse, your certainty about things gets worse.
Well, so then what if your purpose is not to actually find the cleanest sample of QSO,
Yes.
to find the most uniform sample of QSO?
Ah, good. Very good.
Spatially, because you have C,
Good.
which is on the sky.
Ah, good. You brought up an excellent point. And now the rest of the talk will be spent with me answering this point. Actually, it won't, but I'll give you a little flavor for what I would talk about for the next hour if I was going to fully answer that question. And that is that just like in model selection, classification problems always involve a utility. There are some people searching YouTube who want to make sure that every video that's presented to them contains cats. There's other people searching YouTube that want to ensure that if they do enough searches, they will eventually see every video on YouTube that could contain a cat. And you see how those people have very different utilities and you want to do very different things? And in astronomy, it's not sufficient. All these probabilistic models do is give you probabilities. They don't tell you what to do with those probabilities. And different users will do different things with the probabilities. So, and for instance, for some users, certain kinds of spatial uniformity might be very important. Now, I have strong arguments that you can never have the spatial uniformity that you want. But
now you tell me.
actually, I should remind you that when we did this project, we were told spatial uniformity was of no importance.
That's because it's why alpha force quasars as opposed to what we're doing in EBOS.
No, in EBOS, it's
why are you not involved in this in EBOS?
Yes, why not? No,
if you're going to say the problem is not tractable, then
no. The problem's going to be very hard. You're going to have to make decisions about how you even assess that. But yeah, you will have, in general, when you're doing a classification, you should, in addition, good, again, I didn't even say it. In addition to say, I said you should include everything you know about the problem, but in addition to that, you also should include everything you want about the problem. So you should also say, what are my goals, and as precisely as possible, and then build a classification that meets them as well as possible. So I'm confident actually that we can produce a very uniform sample for ABOS. But that will become, that requirement of uniformity will directly affect what we do with these probabilities, how we use them. And we're going to use them in a really weird way in the end.
So, but, okay, so
That's just a great point.
in the bottom part of your example,
Yeah.
the unlabeled data,
Yeah,
certainly some kind of analysis has to go into that so you can actually compare it to the labeled data.
of course, yeah.
So how do you do, without actually, this is completely different, I guess,
Yeah.
without actually looking at a video and watching it and seeing if there's a cat in it, how do you actually do that problem of finding out if there's a cat in the video?
So you will end up, the machine will end up looking at the video. And if, now this isn't a good model for the YouTube cats problem, because the way the unlabeled data and the labeled data differ is not in general noise model.
Yeah.
Like it's not that they just have different noise.
Sure.
But in XDQSO, the way it works is you have a bunch of labeled data, and you know it comes from stars and quasars, and that it has noise on it. What we do is we try to understand the properties of the noise here and the properties of the noise here, such that you produce data sets from the same distribution of stars and quasars.
Okay.
And these differ only because of the noise contributions.
Okay.
So the model we're fitting is this very large flexible model
Right.
that finds the parameters for this stuff such that these two things differ only because of the differences in their noise model.
Okay.
So you can figure, this method is not fast because it involves optimizing parameters all over the place in here. So
Right.
it's a very, very big model. I'm going to come back to talking about big models at the end. But yeah, the way this proceeds is you parameterize or use non-parametrics, which I'll try to talk about. But you do something in here where there's a lot of freedom in here,
Right.
and you set the freedom to make these two things differ only by their noise properties.
Which you input in the first place.
In
Yeah.
XD, we input them in the
Yeah.
first place because we're astronomers and we know
Sure.
them, but there's a generalization of this in which you don't know them, and you learn them as well.
Okay.
Because the fact that the graphical model has a structure that they share this origin is actually very constraining on the noise model, you see? Because you can imagine, like, you can just think of trivial examples where, like, you're just trying to measure the length of an inert aluminum rod, and everyone's measuring it, and people are measuring it by different methods. You can see that you would learn the length of the rod and everybody's noise
Yeah.
model.
Yeah.
Right? Okay, good. That's all I'm going to say about classification, which is basically, if you have this situation, use kernel SVM. If you don't have this situation, use extreme deconvolution, and hopefully you don't have either situation, and then you don't have to think about it. Yes?
The models you're talking about, do these fall under, like making that model from that picture?
Yes.
Does that count as machine learning?
Yes, so at the very end, I was going to come back and say, actually, I've been doing machine learning the whole talk, because drawing this, for a machine learning person, this diagram I've drawn here actually has like this diagram translates into an equation. So in all of it, actually one thing that physicists love is that diagrams equal equations. Like in particle physics diagrams, you turn all these horrifying integrals into diagrams. And similarly in freshman physics, you do these free body diagrams showing the forces and the acceleration. Every free body diagram turns into an F equals ma expression. And similarly here, this turns into a probability expression. So these arrows have to do with conditionals and probability distributions. It says the probability of getting the data here is set by the properties of the noise and the stars and the quasars, but it's not set by the things over here, because things over here don't have arrows into this box. And these are called graphical models, and graphical models are a part of machine learning. And there's a lot of machine learning about building systems that automatically do inference in these graphical models and make approximations in these graphical models and so on. So it is still machine learning. Everything I've said here could be called machine learning. In fact, we publish this as a machine learning algorithm. So it is still machine learning.
And it makes the model and then also labels the data, like, because once you have the model, it's also, it doesn't seem like it would be trivial to take that model and
then label the data.
Yeah.
Well, that gets back to the point that gets back to Tinker's point, that you have to then decide what to do with the output of this to do the labels. And one of the things that's crazy about these methods is these methods don't give you any freedom there. They just label the data, and they just produce labels. And it's up to you to figure out whether you're happy with them. Here, you get the freedom, you'll get probabilities out. So what you get for every unlabeled object is probabilities, either likelihoods or posterior probabilities of it being a star and a quasar. And then in that context, you can then make decisions about what you want to call it. Based on your utility. Here you have no control over your utility. So another strike against these methods on this side is that you can't control your utility. They don't know anything about your noise and they don't know anything about your utility. Whereas here you can control your noise and your utility. Okay, so I'm being deliberately vague about that. I'd love to give a more general talk about utility at some point because I have tons to say about that. In particular, I have a way to compute it. Okay, good. I'm going to just move right along. If I spend that long on the next one, well, it doesn't matter. This is just for fun. Unsupervised. I'm going to call it methods, not classification. So the next category you would say, once you've gotten through your supervised methods, we'll look at your unsupervised methods in machine learning. And the unsupervised methods are methods in which you try to either find structure in data, and these are sometimes referred to as data mining, but I'm trying to own the term data mining in a different context, so I'm not going to write it on the board. But that would be kind of data mining thing. You're trying to find structure in the data without having a model, without having labeled data. You've just been given data and find the structure. Another kind of unsupervised method is density estimation, where you have lots of points in some very large dimensional space, and you want to be able to say what's the density of points everywhere, but all you have are points. Can I have a cup of coffee?
Yeah, sure.
I'm getting parched, and since I'm physically unable to drink water.
There's water in coffee.
There is some water in coffee, as is there water in Prosecco. Oh, Killian missed. He missed. Do you want to smell it? Okay, so these. In some ways, these methods are much more relevant to the physical sciences than the supervised methods, because only a small fraction of problems in the physical sciences come down to we have labeled data and we need to propagate the labels. A lot of what we're doing in the physical sciences is trying to discover stuff, and unsupervised methods are sort of ways to discover things. So the simplest kinds of unsupervised methods would be clustering algorithms. Does your data set look clustered? And that might seem like a trivial problem in a certain sense, but once your data set gets large enough and the number of dimensions gets large enough, it's actually quite hard to assess clustering. So for instance, if you were given the raw data for all the YouTube videos and people said, is it clustered? Of course you should say yes, because it will be for sure. But it's very hard to tell, because you'd be like, well, you'd watch a bunch of videos and you'd be like, I don't know, they all seem kind of different to me. And so the methods to find the clustering or find that certain objects are near others in the space is very interesting. And you might think proximity of points in a data space is very simple, but it's not a simple question. If you have millions of dimensions or billions of dimensions in your data space, it's actually quite hard to find nearest neighbors. All of the videos in a technical sense in YouTube are very far apart. So the simplest clustering algorithms, well, clustering algorithms sort of fall into categories. There's kind of linear algorithms, which they sort of treat the data space. Linear isn't really the right word here. I mean, a computer scientist might be mad to hear that. They treat the data space as given. So in this case, what you're trying to do, the data space might just be large, but you're just actually trying to find separated objects inside the data space. There's there are methods which are called manifold methods, which kind of assume that the data space can be transformed nonlinearly. And one good example of this, treating the data space as given, is PCA, which I talked about last time. In PCA, what are you doing? You're trying to find directions in the data space that are interesting. And so you're sort of treating the data space as real, and you're looking for structure in the data. So PCA is one of these methods that tries to find structure in the data. It's unsupervised. You do PCA just straight up on your data set. And it tells you that there's structure in the data. It says most of the variance is in this direction or whatever. So PCA is kind of in this category. And in this category, the most simple algorithm is called LLE. And I've never used it, although it was written by my best friend in the business. I've never used it. It has been used in astronomy once or twice. And this tries to find a subspace, a possibly highly curved question.
What is this? What is LLE?
Local linear embedding. And it's the manifold, it's the origin of manifold learning, and it tries to find a low-dimensional subspace that you can draw through the data like this, such that if you unwrap it, you get a map with all your data on it. That's kind of what it's doing. I'm not going to talk any more about those methods because I don't understand them yet, and I've never used them. But there's Doug Finkbeiner just sent me an email saying that everybody in the CMB world is, in the Fermi world, is thinking about diffusive maps or diffusive something classification. Anyway, there's a lot of things in this area where people hope that you can run some algorithm and like on your complex data, and then like the quasars will be here, and the pulsars will be here, and the A stars will be here. And there have been some successes in this area. So this is also related to the idea of, you have a very nonlinear data set, can you draw a two-dimensional map of your data? That's kind of also what this is about. Anyway, I don't know much about those, so I can't say very much. But in these linear methods, there's a bunch of really nice things. One very nice algorithm that has not been explored very much is called k-means. It's a very nice algorithm because it's very similar to PCA in the sense that it's looking for directions in the space that are interesting. But what it finds is locations in the space where there are excesses of data points. And you have to tell it, I want to look for the top k places, and then it finds the top k places in your data space where there's overdensity of points. And if you run this on a data set, you tend to find archetypical things. Like, so if you have a data set of like stars and you run k-means on it, you find the common types of stars that appear in your data set. It finds the clusters of stars in your data set.
So, I mean, all of these methods, though, in a way, require you to decide what the parameter space you're searching is. So doesn't that make them somewhat, like, in a way,
well,
makes them supervised? I mean, you know, you talk about density estimation, you have to have
coordinates
to decide what
coordinates.
density.
That's right. So but the way machine learning people think about this is that those should be your raw data coordinates. So you aren't really making a decision. It's what the oracle. Remember my model that the world gives you data as an oracle, and then you're transmitting it over a noisy channel? So the assumption is you do these in the space that the oracle speaks to you in. But of course, in reality, every real experiment, even in computer science, they've made a lot of choices about what data space to do this. And in fact, if you run algorithms like PCA and k-means in the wrong space, you get crap. So for instance, you know, I was saying last time, I don't know if it was last time, but when I was talking about PCA, I was talking about the fact that galaxies are close to linear superpositions of stars, so PCA might be valid. But that means galaxies squared are not a good space to run PCA. So if you just squared all your numbers and ran PCA, you'd get crap. But if you leave them unsquared, you don't get crap. So you are making choices in here for sure. And that's why, and I think the sensible view of all these algorithms is there's a continuum between them. And in fact, this colleague of mine, Sam Royce, who I just mentioned, he actually, one of the main things he did was show that all the different methods that people talk about are actually continuously related.
But you have to look at your data to define a distance, right? So that you can actually say what
Good. Excellent. PCA and k-means, because they sort of treat the data space as given, they are kind of assuming that there's like a metric in the space. Exactly. And all of these methods kind of depend on a metric, sometimes only a measure, but usually a metric in the space, and I barely know the difference between a measure and a metric. Technically, for density estimation, you only need a measure, but for finding structure in your data, you also need a metric. So these methods do have a kind of implicit assumption there, and it's one of my main objections to these methods, actually. Similar to my objection on SVM. You actually know, when you take data as a physical scientist, you know a lot about the space. You know that some dimensions are well measured, some are badly measured. You know that some points are different than other points in how well they're measured. And that implicitly puts a metric on the space that these methods don't know about, which is why these methods will always underperform. Underperform relative to a method like this where you can draw a diagram.
But in other situations, your metric may be totally confusing, and you may have very little information, like videos, for example.
Yeah, exactly. Exactly, and of course, and machine learning, so good, let's summarize. One of the reasons that machine learning, like we opened with the statement that maybe machine learning is never useful in physical sciences, and one of the reasons that you might take that position is machine learning does kind of assume you don't know how your data were generated. You're trying to find an explanation of your data without figuring out how it was generated. And machine learning people are much more focused on prediction. So a very good machine learning problem is of the form, here's the record of what everyone surfed through and purchased on Amazon, predict what the next group of people will search through and purchase on Amazon. That's a great machine learning problem because you sure as hell don't have a model for how people search and click on things, and you really want to make that prediction as well as you possibly can. There's a lot of people here at NYU who work on that problem. They work on it in the Stern School. That's a very big area of research in the Stern School.
But can't you just view it as it's not trying to give you a final answer? It's just trying to bring things to your attention that might be interesting.
Exactly. So one of the reasons, now after bashing it, one thing I would say that's very valuable, especially about these linear space methods, is they often bring to your attention things that are very interesting. So if you run PCA on your data, you often find noise sources you didn't know about. That's one of the things I mentioned last time. And then if you run k-means, you can find groups of objects that are actually very similar. Like it's sometimes surprising if you have a set of spectra, and it would be very interesting to do it on LHC events, to run k-means on LHC events, you'd find events that are extremely similar. And very interesting to find events that are extremely similar according to k-means, but actually that you label differently, and things like that. So it's very good for finding structural problems with your data. So these are good, valuable things, but they're kind of an exploratory. I agree completely, that's a nice point. That's valuable. Now, of course, what do I think you should do instead of these methods? What I think you should do really instead of these methods is build a model for your data, which looks something like this. Data, noise, horribly complicated process. And the reason I write complicated process is you're only actually ever thinking about these kinds of problems in a place where you don't really understand your data. And so if you want to model the data responsibly, you have to understand your noise, but then you have to be willing to put a lot of complexity into this model because you don't know anything about it. And I would say one more thing about this is that actually many problems that I work on, I don't know about people in this room, but a lot of problems I work on look like this. They look like this, where I care deeply about this simple process. I don't care at all about this complicated process, and I know a lot about the noise. So an example is the analysis we're doing of the Kepler data. So the Kepler data is photometric measurements of stars, which very occasionally go, because a planet passed in front of the star. So it's the star is doing some crazy shit, and then occasionally goes, crazy shit. And we're looking for those little divots in the light curve on top of all this crazy shit. So we have to build a huge model for all the crazy shit so that we can find the simple little divot that's in there. And we know a lot about the noise because it's a CCD taking photometry. So we know a lot about the noise. We know how exoplanet transits work. We don't know at all the variable star and calibration problems that are going into the horror. And so we have to put a very flexible model in here in order to see the very simple model we care about. And this, I think, is more like the structure of problems that scientists encounter. In fact, I think this is a very generic structure. And then, of course, if you're a real Bayesian, you would do things like marginalize out this complicated process. Now, how do you model complex processes? Well, there's a lot of interesting ideas in here. Because you can see that the problem with this kind of method, like the kinds of methods we care about, is you have to put a huge number of parameters in here. An exoplanet, transiting exoplanet only has like four parameters, 5 parameters, some very small number of parameters. The star and the instrument might have hundreds of thousands of parameters, well, thousands, let's say it has thousands of parameters, and the data set is hundreds of thousands of pieces of information. So if you just naively approach this problem as a physicist, you would spend all of your time on these parameters and none of your time on these, and that seems like a waste of time. And the first thing I would say is, too bad. You have to deal with that stuff, and you just have to deal with it. But then the second thing to say is that is actually a place where machine learning comes in. There's some very beautiful things in machine learning. One of the most beautiful things in machine learning is called Gaussian processes. And these are a set of very simple models. They're very simple models. They involve a lot of assumptions, but they're very simple models for stochastic processes. And they appeal to physicists. They appeal to physicists because the universe is a Gaussian process. Actually, we don't know that yet, but Tinker thinks we do know that. Remember our little, because you're like, the CME really is created by Gaussian fluctuations or Gaussian, remember? That is a Gaussian process. If you can write down the covariance function that expresses all your spatial and time covariances, if you can write down that covariance, then you can take draws from that very simply. And that permits a huge, you can see how that's a very free model because you're only specifying the covariance structure, not the actual draw you got from that covariance structure. And because everything's Gaussian inside these, they're very, very fast. Well, they're very, very slow, but they're far faster than all the alternatives. But there are other, so that's a very important thing. By the way, the whole point of this is just to give you words that you can look up on Google and not actually try to tell you how Gaussian processes work. I could spend an hour and 15 minutes talking about them. They're outrageously cool.
Why you're saying that? So you want to model your complicated process as a Gaussian process, but usually that's
not complicated
not the
enough.
case.
Right. In fact, I mean, right. To actually have an accurate model of your complicated stuff, like imagine you were trying to understand, I don't know, you were trying to measure like the colors of crops. Like say you're looking at the earth and you're looking down at the earth and you're trying to measure the colors of crops to figure out who's growing castor beans to create rice. Then as your satellite is flying, clouds are going by. So you're imaging down and you're seeing sometimes you're seeing crops that aren't rice in, sometimes you're seeing crops that are, and sometimes you're seeing clouds. And the clouds go by and they're all very complicated, and in principle, if you want to understand your data, you have to build a complete generative model of the clouds as well as the whole surface of the earth. And then all you're trying to do is find out which little patches have the color of castor beans. But you still have to build a model of everything else. Now, you could try to build an exact model of everything else, but then you will spend the rest of your life building a model of the earth and the clouds. If you can live with the fact that your model will not be precisely correct, but will catch a lot of the gross features, then these Gaussian processes work very well. Nothing in the world is really Gaussian, except possibly the CMB. Even the CMB, you know, the secondary perturbations, it's a mess. No, I'm kidding. No, I'm kidding. Yeah, I'm kidding. The Gaussian process, there really does look like the universe is a Gaussian process, which is pretty sick. I mean, if that wasn't true, there are a lot of things you wouldn't be able to calculate. But the fact that you can calculate in the universe shows that you can calculate here. And then we're willing to live with that approximation in other areas just because it gives you a very free set of functions with a lot of freedom, but it's still calculable in finite time. If you want to allow arbitrary higher order correlations or higher order covariance functions, then you can't calculate anything fast. And the other thing that's nice about Gaussian processes is because they're Gaussians. Remember I said as a Bayesian you might want to marginalize this whole thing out. If they're Gaussians, you can actually numerically marginalize, you can actually analytically marginalize them out in many cases. So they really are extremely beautiful.
So, but they're slow because the covariance matrix is like endpoints by endpoints, right?
You
So,
are on it.
so you've got to
Spoken
actually,
like a true cosmologist. You know that there's these things involve in inverting huge covariance matrices. Absolutely. Well, it depends. So we've been thinking about actually whether we could do large-scale structure using Gaussian processes, like literally model the whole observed universe as a big Gaussian process, which would be approximate because in the near field it's very nonlinear, the structure. But still, it's an interesting question whether you could do it. And the big problem we hit is that we can't invert the matrices.
Okay.
However, there's been a lot of work on inverting matrices. And if this talk was not about machine learning, but about applied math, I would talk about linear algebra and optimization, which are two areas where applied math has learned a lot of stuff and that we haven't adopted. So in fact, I think there are a lot of cases where people think they can't invert their matrices, but in fact they can, because they just haven't talked to the right people. So that's an interesting area. If people are interested in that, I know who to go talk to. It's not me, but I know who to go to. But there's other even more hacky things you can do in here. And I can go on and on. There's so many hacky things. But one of them is well, the general name would be called non-parametrics. And the word non-parametric means different things to different people. Usually in astronomy, when people say something's non-parametric, they mean it has a huge number of parameters. I knew Glenn would laugh at that. However, in the strict meaning of non-parametrics, if you're in stats or in your computer science, the strict meaning of non-parametrics is that your model scales with your data. Meaning, as your data get larger, your model gets larger. And it never converts. You always have, if you add twice as much data, you have twice as many parameters, you have twice as much freedom. It's not just that it has a lot of parameters, but the freedom grows as your data grow. But the most extreme form of non-parametrics is actually to just use your data as the model. Which sounds crazy, but imagine the Kepler case that I just mentioned. The star's doing some crazy variable thing. Well, we've measured a lot of stars doing crazy variable things. So you can go to every patch of your data and ask, what's the closest other star in the data set to this star? And use that other star as your model of the data. You can use your data as a model for your data, or other data points as model for your current data points, or whatever. So the most extreme form of non-parametrics is literally just use the data as the model. Now that's never justified, and people get all philosophical about it, it's all crazy, but it can be a very good approximation in some cases. In particular, in that Kepler example, it would be a good approximation. We would be able to find, there's just so many stars measured in Kepler. For any patch of Kepler data, I'm sure we can find many stars that have done the same thing, and we could just use that as our model. We're not going to do that, but it's really fun. You should try it. But anyway, that is, in general, this very complicated process, you have to think about what you're going to do here. And we open by saying, for many of you, machine learning will never be useful. But one place it might be useful is when you hit this state with a very complicated process entering. Machine learning has a lot of ideas about how to model very complicated processes. The other thing is, models with billions of parameters, no problem. People do that all the time. There are lots of, it is a bit of a problem if you think about it. But you can have billions of parameters up here. It is possible. It has been done multiple times.
but not all marginalized over with.
Hell no. Because marginalizing always involves doing something that's at least as bad as inverting the billion by billion matrix.
Right, exactly.
At least as bad. Sometimes a lot worse. Good. So that, but for optimization. And there's a big question about marginalization versus optimization. A lot of people in machine learning disagree exactly on that point. In fact, there's a big, actually the place where the Bayesian versus frequentist divide is largest is in machine learning, because it really affects when you look at this model what you do. Because the Bayesian's like, oh shit, I can't deal with that. Whereas the frequentist is like, no problem, just optimize that sucker. Yeah. Good. I'm sure I wanted to say something else there about that stuff. Well, one thing I could say is that in addition to PCA, there's all sorts of other things that are like PCA that are much better. I mentioned one last time when I talked about dimensionality reduction, but there's lots of others. I talked about HMF, which is the method that I generated, but there's lots of other methods like independent components analysis, there's probabilistic PCA, there's factor analyzers, there's lots of other things that are in the same category as PCA, but much more responsible from the point of view of scientists. And some of those have been used in astronomy. In particular, independent components analysis has been used to separate foregrounds from backgrounds in the CMB.
Wait, sorry, I might have just missed this.
Yeah.
Can you give a less extreme
version of non-parametrics? Good. A less extreme version of non-parametrics would be that you model this complicated, or you model your data essentially as being drawn from a mixture of Gaussians, say. So you fit it not as one Gaussian, but a set of Gaussians. And then as you take more data, anytime the model says, I'm not fitting very well, you just add more Gaussians. So a kind of less extreme non-parametric model would be a parametric model, a mixture of Gaussians, but where you gave it the freedom to just add more components as more data come in. That would be another. Or another would be, you're using up here for your complicated process the levels of bins in a histogram. So imagine in the Kepler problem, we were modeling the stars. This would be a bad model, but we're modeling it as just like we take segments and it's like piecewise constant in segments, and that's our model. That would be an okay model as long as we took more data, we just added more bins. That would also be non-parametric. So those are less extreme. But in general, I think most people in the physical sciences should either go to the nearest neighbor case, like use the data as the model, or go to something that really is a model you can recognize. I think in general, those are, you really want to slam to one of those extremes, I think. You don't want to go play around too much in that area of non-parametric. Although, frankly, the extreme deconvolution falls into that category, because it is a mixture of Gaussian's model, and we do allow the number of components to float. Sometimes, in some versions of the problems we do, and so it is kind of in that category. Okay, good. Let me say. Oh yeah. What else? Okay, good. Let me say a little bit more about density. Well, density estimation just came up because, in some sense, these problems are. These complicated process problems are density estimation problems because you're trying to draw objects from some distribution. But there's even simpler density estimation problems that some of you may have encountered where you have some large data space and you have a set of points and you want to be able to draw the density function from which those points were drawn. That's a very standard kind of problem. One version of density estimation is to make a histogram. But machine learners will all get mad at you. But then the next thing to do is something like a kernel density estimate. And people use these. These have been used in physics a lot in n-body simulations. So SPH n-body simulations, smooth particle hydrodynamics. You're evolving particles in the simulation, but when you want to compute the temperature anywhere, or the density anywhere, or the whatever, the metallicity anywhere, whatever, what you do is you take the points and you smooth them with a kernel, and then you co-add all the kernels that touch the place you're interested in, and the sum of all the kernels that are touching your place is the density of that location. And that's a kernel density estimate. This is a non-parametric density estimate because it just takes the data and it puts around every data point. So it takes each data point, puts a little kernel around it, and the density estimate is the sum of those kernels. It's like a mixture of kernels model for the density. So that's a non-parametric model, but of the density. These are...
The histogram is parametric? Is that what
histogram is also non-parametric if you allowed the number of bins to increase as your data increased.
So why am I going to get yelled at if we use it?
Just because the histogram involves more decision making in a certain sense, because you fix the resolution, whereas these kernel density estimates can be made very adaptive. So as you take more data, you get a higher resolution model. So there's versions of this that are adaptive and non-adaptive. But anyway, if you just have to like take a set of points and make a density function out of them, which many people encounter at one point or another, just use a kernel density estimate. There are much more sophisticated things you can do, but kernel density estimates are basically the best in the business, and they're fast and they're fine. One point is, do not try to do this in extremely high numbers of dimensions. Where high is 3, says Ross. So I would say if the number of dimensions is greater than 15-ish, you should be very concerned. You basically can't have a good density estimate in a high dimensional space. It's just not possible for lots of deep reasons. There is this curse of dimensionality. It's something that comes in everywhere. It's actually one of the reasons that inverting these large matrices is hard. The fact that inverting matrices is hard is related to the fact that you just can't estimate density in high dimensional spaces. There's just no hope. So don't try. So if you get to very high dimensional spaces, you just have to use nearest neighbors.
Sorry, why is the kernel density estimate non-parametric?
It's non-parametric because the model of the density field is the sum of little objects, and there's one object per data point. So if you take more and more data, you have more and more parameters in your model. Most of those parameters aren't free, but they're parameters. Now,
but if you just make the histogram bin size related to the number of data points, you gotta get the same.
Exactly. In fact, and you don't have to make it a very strong function, the number of data points, probably, to do well. That's right. So histograms can be non-parametric as well. But they have to have that freedom to be technically non-parametric. Although I have written papers in which I've called histograms non-parametric, and they aren't. Because non-parametric sometimes just means that there's a large number of parameters.
Just to understand the,
But these are truly non-parametric, deeply non-parametric.
like when I use friends of friends in a body simulation,
Yes.
that is a kernel density.
No, that is a clustering algorithm. So that gets back to the k-means. That's very similar to k-means. When you use friends of friends, you should probably be using k-means.
I don't know what it is.
Right, but if you look it up, it's an outrageously simple algorithm. It's faster than friends of friends, and it has it's more analyzable statistically than friends of friends. Like it has better statistical properties.
Instead, when you use like a spherical overdensity algorithm, these are just
that is very similar to a kernel density estimate. So for instance, sigma 8, in the universe, sigma 8 is roll back the clock to before the structure went nonlinear, take an 8 megaparsec top hat over every dark matter particle in the universe, and coadd. That it's the kernel density estimate of the dark matter density. Well, it's a variance of the kernel density estimate of the universe. So that is a kernel density
specifying that you want a spherical profile.
Exactly. In kernel density estimation, you have to make some choices. You have to choose the shape of your kernel, like whether it's spherical or not, but also its functional form, like how it drops off at the radius. In sigma 8, you're choosing that it's a top hat. But in fact, most kernel density estimates that are well behaved use some like cosine function or something that has finite support, but is
So back in case space.
something like that, exactly.
So it's parametric, but you set the parameter.
Yes, it does have a few parameters. All of these methods have some parameters. The only question is whether they are hyperparameters. Like, so the size of this kernel and the shape of this kernel are like hyperparameters. They go above the model, and you can set them through cross-validation. So in fact, I've written this here to say cross-validation. Because these all, like here, if you do nearest neighbors, you have to decide how many nearest neighbors you use to estimate the density. And so once again, you would use cross-validation to set that number. You have to set kernel things to use cross-validation. Even the histogram, you should set your bin widths using cross-validation. I have a paper saying that on the archive called How to Choose the Bin Size in Your Histogram or something like that. And it uses cross-validation to choose the bin size. We should all do that. I should write an extension to MapReduce that does that. Since MapReduce histograms.
I think Jake Vanderclass already did that.
He probably has. I think he did implement my method. I think he did. Okay, good. Yes? Somebody? No? Okay, where are we at? I could talk forever because there's an infinite number of things to talk about. Let me say some high-level comments. So one high-level thing to say is, if you have enormous, so some things in computer science are related to data being large. So if you have very large data sets, so some people in this room have very large data sets. In fact, some people in this room have the largest data sets that have ever been taken. So if you have large data sets, this is not really a machine learning question. If your data set is large, there's a lot of things you have to decide to do with your data that go beyond machine learning. Like you just have to manage it. Like you have to find it and put it somewhere and be able to access it and things like that. But a lot of interest in machine learning these days is about data sets that are so large they don't fit in your data center. You literally cannot have them all in one place. And one example of that is the LHC Atlas experiment. Produces much more data than you can keep in any one data center. Another example of that is the internet. Although there are a few companies who copy the whole internet, there's a lot that's pretty hard to do as an individual. So if you're studying the internet, you can't really copy the whole thing. We actually here at NYU keep almost all of the astronomical data in the world here locally. Well, maybe not almost all, but maybe a quarter of it. But it means with some expansion we could probably keep it all, but in the near future we're going to get into a state in which you couldn't. SKA pathfinders have turned on, they can't even keep their data themselves. So there's a lot of people talking about data sets that are so large that you can't even fit them in the data center, let alone in RAM or something like that. So then the question is, what do you do? What constraints does this place on you, and how do you perform in this situation? And there's two very important ideas in computer science that I think people ought to learn about if they face this problem. If you don't face the problem of big data, cool. Enjoy. Although these ideas that I'm about to tell you about are so popular that people are using them even when they don't have to. In fact, my group is using one of these, even when we don't have to. So the first one is MapReduce, which is also sometimes called Hadoop, and it has and MapReduce sometimes appears with a trademark symbol, which is an abomination of epic proportions, because somebody's trademarked the name MapReduce.
Can you spell Hadoop or whatever the other?
Hadoop. Because it's also a trademark. I don't care about trademark, but MapReduce. The idea behind MapReduce is your data are separated in many, many machines all over the world. So this would be like the Atlas data. It's separated over, I don't know how many machines for the Atlas data. 100,000? A million?
Machine, well, it depends if you need cores or nodes or data centers. So maybe 100 data centers and then
right, so this is
hundreds of cores for each.
Hundreds of cores. It's really cores that are relevant, because what you do is that if you can do MapReduce, what you do is you do local operations on your data locally. So if your algorithm can be written in MapReduce form. So let me step back for a second. MapReduce is a form in which some algorithms can be written and other algorithms cannot be written. If your algorithm can be written in MapReduce data, MapReduce form, you can run it on a data set of any size. If humanity can keep the data set, you can run your algorithm. If you cannot write your algorithm in MapReduce form, nobody currently knows how you can run it on a large data set. It's just not known. So it's very interesting to separate things you do between MapReduce form and not MapReduce form if you face really huge data sets. The way MapReduce works is you do a local operation on every, so this computer here has a bunch of data, and this computer has some data, and this computer has a bunch of data, and this computer has a bunch of data, and this computer has a bunch of data. Let's do a simple one. Let's imagine these are web pages, and somebody is looking for the most important web page in the world that mentions cats. So what you do is at each computer, you ask, do any of my pages contain cats? Okay, and then you return the most important page. You know, there's PageRank or something, TM. You have some ranking algorithm for pages, and so each of these computers returns its top page that mentions cats, or nothing if it's got nothing. So this has a bunch of web pages, this is a bunch, this is a bunch. Each one looks for cats, and they return out the one that's top ranked, and the rank. And then what happens is you ask, of these two, which one has a higher ranked page? And you output the higher ranked one. And you take these two and you say, which one has the higher ranked page? And you outrank the highest one, and so on.
But again, you have to define a metric for rank.
You have to define a ranking metric. This is why this would only work. It only works for algorithms where you can locally decide whether one page is better than the other.
Right.
If decision of which one page is better than another involves an analysis of all the pages, you're hosed.
Yeah.
You cannot do it. So you have to locally. That's why PageRank was a brilliant invention. PageRank was a brilliant invention because they could rank web pages locally and store the local ranks and never go outside the data center to make the decisions.
But this won't let you find the top 5 pages on the internet, what you just described.
Yes, it will.
Well, what if your second ranked one on the left is better than your top ranked one on the next to left?
Well, what's going to happen? Well, let's see. Let me finish. So what's going to happen is these two will then be compared, and the best of these two will be passed forward. Oh, you're saying you won't return the best 5. I'll give you the example. I'll give you the best 5 example in a second. So these two are compared, and these two are compared, and then these two are compared, and these two are compared, and so on. And do you see how you will now find the best page on the internet that contains cats in log time? Because even though you've fired up the whole data center to do this, like a lot of computers were heated up for this search, but at the end, you just do this log time thing, and then you've got the best page on the internet with cats. Now, if you want to find 5, each of these have to return 5, and then you have to interleave the list. But that's still a MapReduce operation, because you can do it locally with map, and you can do it locally with reduce.
And so, am I going to open a can of worms if I ask you what algorithms what are probably?
Yes, you are going to open up a can of worms. But one example, so for example, I'm now going to talk out of my ass. What I say might be incorrect, but I'm pretty sure methods like PCA do not have a strict MapReduce, but there are forms of them that are approximate that do. What algorithms are definitely are MapReduce? Do you know the answer to that? One algorithm that's MapReduce is computing a likelihood. You can compute a likelihood in MapReduce because what you can do is you can compute the likelihood for every single data point, and then you just co-add the log likelihoods, and then you, assuming you have independent data, you can compute the likelihoods of all your data points, and then you can co-add the log likelihoods locally, and then you co-add, and eventually get the total likelihood for your whole data set. You can also take derivatives of a likelihood in MapReduce, because there's a derivative of the log likelihood for every data point as well. You can take all those derivatives locally, and you can pass up all the derivatives. So, what are you laughing at?
So you're spilling so much coffee, like, oh.
I know, and it is your handiwork. I apologize.
Is there a non-ranking, because like if it's just a ranking, is there a non-ranking application that's MapReduce?
Wait, I just told you two. Computing the likelihood
but like
and computing gradients of the likelihood. No, I'm saying you can compute the gradient of the whole, like with your whole data set, you could take the gradient of the likelihood of your whole data set with respect to a parameter in MapReduce.
So basically, any operation that requires only analysis of one data point can be MapReduce.
No, as long as those are all combined locally.
As long as they are combined linearly.
Exactly, in some simple way, or simple enough. So as Dan just said, you can count your data under MapReduce. And in fact, that sounds like a trivial operation, but a lot of database queries in this world are just how many objects meet these criteria. And the database is split over all these things, and they can return that answer really fast. And of course, one of the reasons that Google has been such a successful company is they return search results fast. And if you go back, we all forgotten the annals of time, but when it was like Alta Vista, you would just sit and wait for your search results. And then they came fast with Google, and why were they fast? Because they formulated it in this form.
But it's not this specific.
It's very close to this.
Really?
They do something slightly more sophisticated, but nobody has any idea. Actually, several companies have said in my face that if they cannot run a model, algorithm MapReduce, they cannot run it. They won't run it. Google has said that. Yahoo has said that. IBM has said that. Somebody else has said it in front of me too. Anyway, several companies have said, like in public forums I've been in, that if you can't do it in MapReduce, you can't do it. Which means if any of you has a way to do calculations at scale that isn't MapReduce, you're going to be infinitely rich. Like it's the best place to make money right now. Because it's not like you'll start a company. You'll start all the companies.
But would it be actually better than the search results that are returned by Google?
But you create all sorts of things beyond search that you could do. Because search, the reason search is such a valuable thing is because it can be done fast. If new things could be done fast, they would crush search.
Maybe, and this information is really public, that Google use this really public.
Yeah, in fact, they have developed these tools. I think Hadoop is a Google brand, isn't it?
Well, the closely guarded secret is the page rank, not the...
Yeah. It's the details. There's two important things that Google has that they won't share with anybody. One is the details of how they actually rank the pages, and another is the details of how they set up their data center. And a lot of it's in the details. You can do this badly and you can do this well, and that's orders of magnitude of performance.
I do lucky imaging with MapReduce on the cluster, but I didn't know that.
Nice. You didn't even know it was MapReduce. Yeah, lucky imaging. Actually, a lot of image analysis things are MapReduce, or can be written in MapReduce form. So MapReduce is a valuable thing for physical science, actually. It's not machine learning, but there it is. That isn't machine learning. That was, sorry, I failed. There's one, data structure, but it's related to machine learning because a lot of machine learning and research is how can you transform algorithms into this, and can you transform approximate versions in? So there's a lot of things where an approximate version can find MapReduce.
If you wanted to do something like find the closest pair of data points, would that be an example of where you're screwed?
You might, well, yeah, you would. I think the closest pair is you're screwed. I think you can't do it.
Because you have to compare pairs
exactly.
across all.
So then I think they do.
But if you want to find the closest point to
a particular point, then you can find it.
Yeah.
But so then there are these very clever things about hashes. Like one of the hashes are a big thing in the computer world because sometimes you can transform problems like that into problems of like hashing and get approximately 2 points that are likely to be in the top n closest or whatever. So that's this kind of thing where people look for approximate algorithms here. That's exactly a good example. Good. The other thing I wanted to say that people do when they have very large data sets is something called online or stochastic. And here the idea is your data set, and this is also relevant to lucky imaging, but here the idea is your data set is a set, you have a set of data that's coming through so fast. So the idea is you have a data stream coming through, and it's coming through so fast you can't actually look at every data point. You literally don't have time. You probably don't even have time to read it. So and this is why they're called stochastic methods. What you do is you just take the next data point you get a chance to look at, and you use it to update your model. And then you throw it away, and you take the next data point you can grab, and you use it to update your model. So you don't optimize on all your data at once. So usually when you do, usually in the kind of data analysis we've been talking about in this course, you're asking what's the probability of the data given parameters, where this is all the data. So this is actually some product over n data points, the probability of the nth data point given parameters. And then what you do is you try to find the best parameters, like the maximum likelihood parameters. But because this is just a product of these probabilities, you can write that as a sum, the log of this. You can write as a sum over n of the log of these probabilities. And then you can see, because this is a linear sum of log probabilities, there's the derivative of this object will be a linear sum of logarithmic derivatives of the log probability. And so you can actually you can figure out the derivatives in your space without actually looking at all your data. Subsample of your data, a random subsample of your data is going to tell you what the gradient is, at least roughly. I mean, it won't be exactly right, but it will be close to right if you have a random subsample. So if you believe that your data are being produced by a stationary process, you don't actually have to look at them all simultaneously. You can look at them sequentially or randomly and still optimize to your optimum. And so this is another big area of research in machine learning these days, which algorithms can be converted into an online form. And in fact, a standard question if you go to a machine learning conference, people will ask is there an online version of that? It's like the magnetic fields question in physics, in astrophysics. And in fact, a very large number of algorithms have an online form. And like, for instance, PCA, I believe, has an online form. But this is, again, it's not relevant to a lot of us because most of us save all of our data, and we should. But it's a very interesting question for like a next generation particle physics experiment that's throwing away a lot of data. could that, even though it's throwing away the events, could it save some kind of gradient information from the events? That's an interesting kind of future thing for people to think about. Okay, I'm going to stop there. I'm done. God, who put out that coffee on the wall?
Maybe in the beginning you said that there is a way to do what we do in particle physics. You go from a graph to an equation.
Yeah, a graph to an equation.
Yes, suppose I want to
go from this graph?
Play a pretty simple model, let's say for, I don't know, a set of web page and try to write down an equation that can do all the, is that possible?
I don't know. So I haven't thought about whether this graph here relates to an equation.
It does. It relates to
It should be, but
a sum.
It is a sum.
Right there. It's that equation.
It is. It's this equation. That's true, actually. Yeah. Yeah, but
this is not so deep.
No, that's not very deep. The graph.
Not very deep.
No, the graph.
I mean, the sum over argmax.
Yeah. MapReduce is not deep at all.
No, it's not. Those aren't deep. But the graphical model question is the graphical models are more deep. So in a graphical model, I'm not going to say anything very good here. But imagine there's a set of parameters. This is some big vector of parameters, which is like the variability of your star. And then there's a smaller set of parameters, which are the parameters of your exoplanet. So this is like the period and size and inclination and stuff of the exoplanet orbit. And then these parameters are about the variability of the star and the variability of the system. And then there's some parameters which are about your noise in your observations. Like maybe this is the per observation variance in the Gaussian noise. So you can take these parameters and you can predict, those parameters will predict the flux observations, Fi, that Kepler has made. So Kepler has made a whole bunch of observations, each of which is a brightness of the star. And the brightness is affected by the variability of the star, but also by this exoplanet which occasionally eclipses it, and then there's noise contributions. Okay, so this would be a very simple graphical model, and this box is over observations. This graphical model turns into an equation.
Can
the
you write
equation
that
it turns into is the probability of the data given alpha, omega, and sigma squared is the product over I, P of Fi given alpha, omega, sigma squared. Now that's a very trivial equation that we produced, but let me just say a little bit more, and then I'm going to make the graphical model slightly more complicated. And then this will show you what Foreman Mackey's project is. So all this says is that Fi depends on these three things. That's what the arrows mean, and the box means there's multiple observations. And those observations are independent. So the independent observations can be producted together, and here are the dependencies. This depends on this. Okay? Now, Foreman Mackey's project, if he chooses to accept it, will be to compute not the properties of an individual exoplanet, but of all exoplanets. So there's some really big function which says, what's the distribution of planetary radii and periods and inclinations and so on in the data set that produces for each individual planet its particular values. So now that exoplanets will be n, each exoplanetary system is affected by some variability things and it has its own parameters. This is now Fin, this is the ith observation of the nth exoplanetary system. And now this is a much bigger object, because now there's this new dependence here. So now you have to multiply P of omega n given omega, and these now become n, and these are this noise model. Let's just leave it as a simple noise model for now because it's too complicated. And now, if I want to do the probability of all the data, I have to do this outer product over all the n systems. But then you can also do marginalizations here, because now you might say, well, I don't care about these individual things, and I don't care about this noise model, this stochastic process. I only care about the population parameters. And then this sort of model also implicitly says that you can now do integrals. So you can do some horrible double integral, which is d omega n, and then you could put in a p of alpha, d alpha, d alpha n, d alpha n. And that would imply that alpha n is generated by something out here, who knows what. So, and this whole expression is implicitly contained in this model.
Now the small makes a big related big and alpha.
Ah, good. Yeah, yeah. Sorry, I totally screwed up. This, now I've integrated out omega n and alpha, but I've left in this omega, so this now became this. Good. So, yeah, so that's the sense in which these diagrams turn into equations. And actually, computer scientists often talk to each other just in terms of diagram. So they just never write this down. There's a lot of papers that are a little weird because they're like, figure 3 shows the model we're computing. And then there's no equation anywhere. And you're like, what the hell is the equation? Because the equation is implied in here.
So by nth exoplanet, you mean nth star?
Actually, here I really mean nth stand. So this really should be exoplanetary system.
The potential exoplanetary system.
Yeah, exactly.
Because the model must include the possibility that there's no planet.
And then this allows then of course this is some weird object that can have more than one exoplanet or 0 exoplanets. Yeah, exactly. And this prior allows that multiplicity.
So doesn't it imply that you have a lot of observation for the external exoplanet?
This doesn't directly imply that, but usually that writing it this way makes more sense if you have many observations per system and many systems. Oh shit, yeah. I mean, in Kepler, there's like 100,000 stars, each of which has hundreds of thousands of measurements.
Oh, wow.
It's been staring at the same ones for a long time. It
It's
doesn't change
huge.
anything. It's just looking at the same stars.
Oh, I see.
I mean, it's at the level that we might actually have to think about things like MapReduce. We try to avoid thinking about such things, but we might have to. Yeah, it's big, really big.
That's funny because you could
We
then
need a roundup about Kepler.
you could model the entire Kepler data set as a single Gaussian process, and it would still be faster than modeling just the CMB as a single Gaussian.
That's true, yeah, because the CMB is a really large map.
Millions by millions, right?
Yeah. Yeah, no, that's right. Actually, data sets in astronomy have really gotten large now. But yeah, that makes me think we should have round back about Kepler. You want to give one? Okay, good, I'm done. We're dismissed.